Okay, so I am very glad to announce the talk of Saul Friedberg from Boston College on a new theta correspondence.
Okay, thank you. First of all, I'd like to thank the organizers very much for the chance to give this talk. I've had the pleasure of being at Weizmann since actually 1979, 1980, when I spent a few months there while I was in grad school. And I've been back many times over the years, and in particular in the last few years, though I haven't given a talk, I've had a lot of wonderful one-on-one conversations, in fact, with organizers from the seminar, and they've been great mathematical conversations. So I appreciate the chance to be here. For those that can't read Hebrew, that says Boston down there. And that actually is a picture which has something in common with the Boston of Boston College, namely the Boston College, which is on my screen, and the Boston in that picture, neither of them are in Boston. The one on the bottom, of course, is in Israel, in Tel Aviv, and the one on the top, Boston College, actually isn't in Boston. And just to add to the Michigan, it's also not a college, but Boston, you can never become Boston University because that's a different place, and it's been Boston College for 150 years. So anyway, so we go forward. Okay, so to the math. Here's the plan for the talk. The talk actually has a lot in common with the last three lectures from Steve Miller, Dima Gurevich, and WITech. And so the first part of the talk will review some aspects of prior work that will fit into the new work. And so I'll begin by talking about the classical theta correspondence. Of course, WITech gave a wonderful description in the context of his talk last week, and this will just be a quick informal review. And I want to say that, as I'll explain, it's an incomplete review. And so if there's work that I don't talk about that you think I should have, I deeply apologize, and I'll sort of explain why it's an incomplete work in the course of the survey. And then talk a little bit about going beyond the WIS representation ideas that David Kajdan brought into the subject a long time ago that have been developed by a number of people that I'll mention, and then talk a little bit about non-minimal theta correspondences, again, some older work and then a little bit more recent work. And that hopefully all of that stuff will go relatively quickly and bring us to new work, which is joint with David Ginzburg from Tel Aviv. And the idea is to extend the classical theta correspondence to higher degree metaplectic covers. And my goal isn't to go through the details of the proofs, but to give you the structure, because it's the new structure that gets involved in making that work. Okay, and WITech, I think you had 33 slides last week, so I'm up to 34. So, but hopefully I'll talk quick enough that we'll get through them all in a reasonable time. I think that'll be the case. Okay, so very quick review of the classical theta correspondence. I might start with a vector space V and look at its special orthogonal group. It's equipped with a symmetric bilinear form, and then W prime equipped with a symplectic form, and look at SPW prime, and then take the tensor product of the forms and take the tensor product of the vector spaces and review W as equipped with a symplectic form coming from that tensor product. And this is the classical construction, and G and G prime become embedded as subgroups of SPW when we do this. And this leads to the theta correspondence, which again was WITech in particular talked about last week. I want to focus mostly on global aspects, so there'll be local aspects I'll mention too. And so globally, you can you can make a theta function, and I'll talk about the representation in a moment, on the double cover of SPW, the big symplectic group, and use that theta function or family of theta functions as integral kernel of automorphic forms on the group G and move them to automorphic forms on the group G prime by means of an integral kernel. So in order to do that, the kernel that you integrate over has to be automorphic for this to all make sense. And the automorphicity of a theta series classically was proved essentially by Poisson summation. And the thing to keep in mind about these theta series that are integral kernels is that they have many vanishing Fourier coefficients in a way that we'll make precise later in the talk. But sort of even classically, they're built out of, in some sense, sums of squares or values of a quadratic form on a lattice. And so there are many vanishing Fourier coefficients. So that's the classical theory. Okay. And so, for example, a first case of this goes back to the Shimura correspondence. And if I do an odd orthogonal group, then in fact, it's really the metaplectic group that's involved, and so it picks it up, and the theta kernel gives you something of half integral weight. And of course, this was analyzed by Shintani and Niwa classically, and then adelically in representation theoretically by Weil. And it led to all sorts of beautiful work, and in particular understanding that the theta correspondence captures central values of quadratically twisted L functions. Okay, so going back to the group theory for a moment, and again, I'm doing this quickly, expecting people already are very familiar with this, that if G and G prime are act reductively on a vector space W, and each is the full centralizer of the other in SPW, then they make a reductive dual pair. Okay, and so I'll be generalizing that algebraic setup a bit later in the talk. Okay, so I thought, when I started this, that I would give a little quick introduction to the theta correspondence, and I took the step of looking in Google Scholar and discovered that there were 271,000 entries about for theta correspondence. So that's why I'm not doing them all. But in particular, I wanted to mention the work on theta towers of Steve Rawlis, who says that we don't just look at the way SPW pairs with SOV, but we actually look at a tower of orthogonal groups by adding one or two or n copies of a two-dimensional hyperbolic quadratic space. So if I was in an Archimedean setup, I might not just look at SO21, but SO32, SO43, SO54, and so on. And so, for example, if you start with an automorphic representation of SPW, then Steve showed that there is a non-zero theta lift in this tower, and that the first occurrence is cuspidal. There's also a local statement that was proved by Steve Kudla. Now, the question of exactly when you get the first non-zero lift in the tower is called the first occurrence, and that's of interest and related to periods, worked out by Brooks Roberts in some detail. And you also can ask about this theta correspondence with regard to the wavefront set, in the sense that Dima talked about, for example. And David Ginzburg and Nadia Gurevich made some statements about how that works with how the theta correspondence works in terms of wavefront sets. Okay, so that's a quick review on the classical theta correspondence, at least globally, and then there are local aspects as well. And as we all know, the local object that's relevant is the Weil representation, which requires choice of an additive character. And they explain the theta series really come from this Weil representation on the metaplectic double cover of the symplectic group. And in fact, the How correspondence, which again was discussed recently in the seminar, was formulated by How working over a local field. And he conjectured that omega psi restricts to a correspondence of local representations in his 1979 paper, Theta Series and Invariant Theory. And that work was proved by How for Archimedean fields, by Waltz Berger for non-Archimedean fields of odd residue characteristic, and by Witek, Gan, and Shuichiro Takeda for arbitrary residue characteristic. And so then you ask, well, let's just do a survey of the How correspondence, and it turns out that that even beats the theta correspondence, according to Google Scholar, with lo and behold, 364,000 results. Something I wanted to mention that will come up in the other work too is that this correspondence is functorial when the size of the groups is roughly the same. Rawlis, Adams, Prasad certainly contributed to that, perhaps others as well. And that there's, again, a local interaction with the wavefront set studied by Moglan, Gomez, Chengbo Xu, with respect to models, Beiying Liu, and undoubtedly others as well. So just a quick account of what's at stake in the theta correspondence. And again, I'm missing many, many aspects of it, but just to give a quick survey. Okay, so maybe the next step is to go beyond the Weil representation. And so maybe the question is, why is the Weil representation so special? And so the context here is if you're given two p-adic groups G and G prime, and they both sit inside a larger group H, and you take a representation, say an admissible representation of H, then you certainly can attempt to study its decomposition in some sense into irreducible representations of G cross G prime. And the way that goes is if you take an irreducible admissible representation of G, then you look at the maximal pi isotypic quotient of theta, And this is what Wojtek talked about last week, and it's the big theta in the context of his talk, and that maximal pi isotypic quotient is of the form pi tensor theta of pi. But when you say it in this generality, I mean, maybe theta of pi isn't even of finite length. So theta of pi might not, be a nice object. But if it is a nice object, then the intuition is that the big theta on the big group must have been small in some sense. And I think David Ginzburg, who's here in our seminar, I believe, a long time ago said that the relevant thing to focus on is that the Weil representation is a minimal representation. It's attached to the minimal non-trivial coadjoint orbit. And I'll say a little more about one way, at least, of thinking about that a bit in another slide or two. But the question, which again is an old question, is can you find other minimal representations? And so you can ask locally, can you make a generalized Theta correspondence for them? And you can ask globally, can you find other automorphic minimal representations and use the functions in the space of that representation as theta to make a theta kernel and write down an integral that's analogous to the integral for the classical theta correspondence. And again, this is an old story. So I'll try to just to give a brief mention of some of the work on that, but it plays a role in what comes later, and it's beautiful, important work in its own right. So let me go ahead to that. And so let's see. So let's talk about it first locally and just formulate it. The unipotent orbits come up in many guises, and I'll just think of them in some senses as being attached to partitions which index a family of unipotent subgroups, and then to each one of these unipotent subgroups, there are some generic characters in a suitable sense, and I'll call psi-O a generic character of UO, and then you can form the twisted Jacques module attached to that unipotent subgroup UO and that character psi-O and form that quotient. Just a word of caution that for the Whittaker case where U is the unipotent radical of the Borel split, say, then all these characters are a conjugate under the maximal torus in a favorable situation, but that's generally not the case. So there might be orbits of generic characters. Okay, and so minimal in the context that I'm going to use it is that the unipotent orbits are come equipped with a partial order, and so you can ask that any unipotent orbit beyond the minimal has twisted Jacques module 0, and that's for any generic character, and that would be a minimal representation. You can also talk about it in terms of Gelfand-Kirillov dimension being 1/2 the dimension of the minimal coadjoint orbit. Okay, and as I think came up in Dima's talk, this can also be talked about in terms of the character distribution chi-pi and the Howe-Harish-Chandra expansion. And just that won't play a big role in our talk, but I'll just mention that Wojtek and Gordon Savin have a nice paper where they explain and talk in some detail about some of those connections in representation theory from 2005. Okay, and then in the context of local minimal representations, Gordon Savin, David Ginzburg and Gordon Savin studied local minimal representations and constructed them, maybe Tarasso in one case as well, Archimedean work of Gross, Wallach, Berlinski, Kostin, and probably others. So locally, at least, that's an account of probably a part of the story. And then we can go in the automorphic context. And so there, the way I think to think about that is to start from the theta series, which come from the Weil representation. And it's an old observation that the theta series, which appear in the as kernel functions in the automorphic theta representation, can be realized in another way that doesn't see the Weil representation. Namely, they can be realized as residues of Eisenstein series. So one could construct them without having the Weil representation. And that statement is really a special case of the Siegel-Weil formula. And some papers of Ikeda, I think, flesh that out and give a lot of detail and explain it. And so the idea is to use other Borel-Eisenstein series and to construct residues of those Borel-Eisenstein series and call those objects automorphic theta representations. And sometimes those might be minimal representations. And again, I want to emphasize there's no Weil representation. There's nothing like a Schrodinger model one can use. But on the other hand, one can write down the automorphic objects and the local objects that are attached to them. And so using this idea, residues of Borel-Eisenstein series, David Ginzburg, Steve Rawless, and David Sudri in 1997 in the Israel Journal constructed automorphic minimal representations for split simply laced groups over number fields. Okay, and with that, one can go ahead and start to work with exceptional theta correspondences, and this won't play such a big role in the talk today, though maybe it's a direction for some future work. But just to mention again, a subset of the work, and I apologize that it's incomplete, but Maygard 7 in 1997, the non-Archimedean local correspondence for the minimal representation of E7, restricted to G2 cross SP6, John Schuley in the Archimedean case, Dick Gross and Gordon 7 have an automorphic version, which is related to motives of rank 7 and weight 0 over Q, the Galois group of type G2. Marty Weissman in his work in 2006 gives what he calls an octonionic version of the Jacquet-Langlands correspondence. There is other exceptional work, Archimedean work, you can see in 1996, all the way to 2019 of Loke and Savin. And then looking in, from, again, back in the automorphic sense, Ginzburg, Rawless, and Sudri even made the theta tower construction work. They found an automorphic theta tower, which involved G2 by using the automorphic minimal representation of GE7, and some further work of David and Diwa Zhang in the Israel Journal in 2001. And then going to the exceptional group F4, David Ginzburg in Journal of Number Theory in 2019 has a long paper where he uses the automorphic theta on the double cover of F4 to give a theta correspondence. Okay. So, so here's the double cover, and maybe it's a good time to talk, just to give one slide about metaplectic covers. So I'm going to be using covers, and so I'll be concerned with the following context. And let me let R be greater than 1, and it'll typically, well, okay, R will be greater than 1. It'll look at a local or global field which contains a full set of R3 subunity. And then underline G will be a linear algebraic group over F. And I'll either be looking locally or adelically, and I'll write G without the underline for one of those, depending on the context. And then in various ways, you can construct a topological central extension of G by mu R. And there's, again, a very, very long story of this, which I'm not going to give all the details of, but the extensions can be understood categorically, and that was done by Berlinski Lean, giving an extension where the mu R is replaced by K2, and then you can push out to get this extension. And then some recent references are a paper of Fan Gao with Witek and Marty Weissman in 2018, their whole asterisk volume. And then Eyal Kaplan has a very nice paper from 2019, which uses actually a lot of the language that we're going to follow in this paper. And so those are just a few of the many, many references about this. Okay. So I now want to talk a little bit about non-minimal theta correspondences. And again, some of this is old work. And it starts with an observation of David Vogan that there's no minimal representation. You can't find a representation whose Galfand-Kirillov dimension is the desired one if you're looking with a split odd orthogonal group for SO9 or higher. So when 2n plus 1 is 9 or higher, you can't do it. And so together with Dan Bump and David Ginzburg, we actually were able to construct an automorphic representation on the double cover for split SO2n plus 1 that was still small in a specific sense in terms of the unipotent orbit, but was not minimal. And small for SO9 meant that beyond the minimal orbit, it's a partially ordered set, and there are two incomparable unipotent orbits that sit over the minimal one, and this was attached to one of them. And I should say, by the way, that some unipotent orbits are special, and for when you're not working with covers, automorphic representations deserve to be attached in many contexts. The special orbits but actually that's not true for these orbits. So this is a theta whose unipotent orbit is not a special orbit. Okay, so nonetheless, you get it as a residue of an Eisenstein series, and you can prove that it's L2 and irreducible. And locally, you can construct the local representation in a way which is familiar. That goes back to the work of Kazhdan and Patterson, where they studied covers of GLN. And locally, you can get it either as a sub or a quotient of an intertwining operator attached to the long Weil group element, where you take a certain suitable character. And so it's either a sub on one side or an irreducible quotient on the other. Okay. So in this old work, and again, it'll have some relation to the new work, so I want to just mention it for a slide or two. The unipotent orbits here, just to give you the exact story, they correspond to partitions of 2n plus 1, such that every even part is repeated an even number of times. And so you end up that the unipotent orbit is the one attached to the partition shown. This is, again, a theorem from 2003, that this is specifically the unipotent orbit. So it's a relatively small orbit, but it's not the minimal orbit. And what I mean by that, this is the orbit attached. I mean, I've been using that without explaining it in an adelic sense. And so globally, you can write down Fourier coefficients attached to each one of these unipotent orbits and any generic character for that unipotent orbit. And when I say that it's attached to this, I'm making two statements. One is a vanishing statement, that it has 0 Fourier coefficients for any unipotent orbit that's either larger or incomparable. So vanishing for those. And also it's a non-vanishing statement that there is some non-zero Fourier coefficient attached to some generic character on that unipotent orbit. Okay, so then we also had some local results. Okay, and then just to describe how you make a correspondence, it's sort of surprising. Maybe you can do a non-minimal theta correspondence, and you just embed an even and an odd orthogonal group in a bigger orthogonal group in a sort of very mindless way. You just embed it by blocks, and you can then take the theta representation, this small but not minimal theta representation, and restrict it to the image of the two subgroups. You have to do this with covers, and you can make that very precise. And you integrate against something on the double cover, and say of SO2K plus 1, and you can produce something on SO2M. And so we did this in 2006. And we show that it's functorial in a suitable sense. And so maybe just to say a word about that, at that time, there wasn't a formal definition of an L group, but we wrote something down in 2006, and we talked just about the connected L group, and these are all in a split case. And we said that the connected L group works exactly for odd degree covers like it does for the 1 degree cover, but for even degree covers, the long and short roots sort of swap in some sense. So for odd degree covers, the connected L group is SP 2kc, but for even degree covers, it's actually SO2k plus 1c again. And in that sense, we got a functorial correspondence. And in particular, when the ranks were close, then we got a functorial correspondence. And you might ask, can you then talk about, say, the way the wavefront set works for this non-minimal theta correspondence, a bit of it, or of an exotic object? And my grad student, Yusheng Lei, has actually just really gotten some results on how the wavefront set interacts with this non-minimal theta correspondence. And there's probably much more that one could do locally as well. His results at the moment are actually global, similar to what Nadia and David Ginzburg had. And then I think there should be some nice local results as well. Okay, so there's actually one more minimal theta correspondence that I wanted to talk about. And that's a recent one of Spencer Leslie that was published in 2019. And what Spencer did is he looked at the automorphic theta representation on, of all things, the fourfold cover of a symplectic group. And 4 turns out to be necessary. It doesn't generalize beyond 4, at least as stated. And so he was able to show that this theta representation, once again, is not minimal, but as small. And he was able to find the exact unipotent orbit attached to that theta representation. And then he was once again able to embed two symplectic groups in a bigger symplectic group and use the theta function on the bigger group as an integral kernel, and even make the tower property work. And so what he showed is there is a tower property, and that the first non-zero lift of a genuine cuspidal representation is a cap representation. So that's what happens in this context. And in fact, he also worked with Arthur parameters a bit and showed that it all really fits the expectations. And he also studied the local correspondence for unramified principal series. Okay, so that's all the survey. And I was hoping that that would be about the first half. So maybe I'll just ask, are there any questions before I go on to the new work or comments?
Could you please remind what is a cap representation?
Cuspidal almost parabolic. Oops. So so it's a cuspidal representation, but almost everywhere it looks like an Eisenstein series. Okay. Okay.
Excuse me?
Yeah.
And if you consider this theta, does there exist such a theta 2m representation corresponding to the same orbit on this algebraic group? I mean, why did you have to go to the covering? I mean, why did Spencer Leslie had to go to the covering?
Right. So I don't know if there's such a thing for the group. I mean, I know we know how to get this by a residue of an Eisenstein series, and that construction certainly wouldn't work. And then, you know, Steve Miller in his talk was giving a whole bunch of objects that should exist that I don't think we know how to construct. So I don't know the answer.
Okay.
Good. Okay, any more questions or comments? Okay, so now I want to talk about this new work of extending the classical theta correspondence. And it just came out on the archive very recently. And again, it's joint with David Ginzburg. And the work will be to extend the theta correspondence to all odd degree covers of orthogonal groups and corresponding covers of the symplectic group. And so in the rest of his talk, R is going to be odd. And so we'll do this, of course, both locally and globally. And so here's the dual pair, SO2A. The even groups pair with the symplectic group. There's no double covers. And so we'll pair the R-fold cover of an even special orthogonal group with an R-fold cover of a symplectic group. And then if it's an odd orthogonal group, because the Weil representation lives on the metaplectic group, it pairs with the double cover of the symplectic group. Again, just going back to that Shimura correspondence example, SO3, SL2 double cover. And in a similar way, we'll be pairing SO2A plus 1 R-fold cover with SP2L 2R fold cover. So that's the construction that we're going to give. And I want to give now the algebra of the construction. So this is a slide with a lot on it. I'll go over it slowly. And just to say what's going on, that in the paper, this isn't laid out quite as clearly as it is in this slide. And I actually sent the paper to Roger Howe, and he said it wasn't as clear to him as it could be where the algebra was. So then we wrote this as a little addendum, which is not only in this slide, but you can find it on my webpage if you go to publications 2010 on. It's right next to the place where this paper is referenced on the archive, and it will get rolled into the next draft of this paper. But if you want to see it and you don't want to go dig up these slides at some later time, it's also on my website. Okay, so here's the construction. This is the algebra behind it. So I'm going to start out with two groups, G1 and G2, reductive groups, say, and two symplectic groups, SPW1 and SPW2. So there are two different symplectic groups at play. And for the first of them, there's just an injection from G1 cross G2 to SPW1. But there's also an injection, and that'll be sort of familiar. There's also an injection iota 2 from G1 cross G2 to SPW2. So two different injections. And by the first map, G1, G2 is just a reductive dual pair inside of SPW1. Just the familiar thing that we're all used to. Okay, and with respect to the second group, it's not true that G1 cross G2 is a full reductive dual pair, but it is true that the images of G1 cross the identity and G2 cross the identity commute with each other, but they don't have to be the full centralizer. They might just be a piece of the centralizer. Okay, so we need a little bit more structure to rigidify that. And the extra structure, which will be very familiar to anyone who's read all descent integrals, is to take a unipotent subgroup of SPW2. And that unipotent subgroup is normalized by the image of G1 cross G2 inside of SPW2. So when I conjugate by the image of G1 cross G2, the group U is preserved, just under conjugation. And along with the group, there is a character. Okay, of course, globally it's of the adelic mod rational, or you can do it locally. Okay, so there is a character of the group, and the embedded image acting by conjugation stabilizes the character. And it may not be exactly the full stabilizer, but it's pretty close, that it's a finite index in the full stabilizer of psi u, inside the normalizer of u inside of SPW2. Okay. So that's the structure there. So I have G1 cross G2 sitting inside SPW1 in the usual way as a reductive dual pair. And then I have this structure, which is maybe familiar from descent integrals inside of SPW2. And then there's also a connection. There's a homomorphism U, script L, which takes U, which is inside of a second group, and moves it to the Heisenberg group attached to W1. Just the Heisenberg group, some people call it extended Heisenberg group, attached to W1, just by extending by the symplectic form, the usual way. Okay. Okay, so that's the structure. And I'll give explicit example of this a little bit later, but that's the general structure. Okay, and now here's the representation theory. So for the first group, we have a reductive dual pair, and we simply take the Weil representation. So locally, we choose an additive character, take the Weil representation. Okay, globally, we'll make theta series, of course. Okay, and on the second group, SPW2, and really it will be a cover of SPW2, of course, we'll take a small representation. And here is where, in the same sense as before, I'll take something that's small. It's certainly not generic. It's not attached to the largest unipotent orbit, but it's generally not going to be minimal, but it'll be a small representation of SPW2. Okay, and I'll take the tensor product and think of that as a representation for the Heisenberg group semi-direct product with the double cover of SPW1. So SP tilde is really the metaplectic double cover. And then SPW2. And again, really we'll be doing this with some extra covers floating around, R-fold covers, 2 R-fold covers. I won't really keep track of all the covers in the talk. I'll write it all down. It's all written down very carefully in the paper. I'll say a little bit about it. But this is the algebraic structure. And with this structure, the idea is we're proposing that, in favorable circumstances, there should be locally a generalized Weil correspondence and globally a generalized theta correspondence. And so that's the proposal. Okay, so let me give some indication of what I mean by that. So let me start with locally. So locally, the Weil correspondence, you simply take the Weil representation and you take the pi isotypic component in the sense that we talked about. And here we have this unipotent group U. So instead of just taking the tensor product of the Weil representation with the small representation theta2, and then attempting to take pi isotypic components, we have to pass to a twisted Jacquet module, which takes into account U. And so the idea is that for U and U, the thing I mod out by is just the kind of thing you would mod out by to make a standard twisted Jacquet module, which I wrote down earlier in the talk. So there would be, the action of U on the vector minus the character of U times the vector. And that's what happens with respect to the second representation. But there's a first representation, and there we take that homomorphism that moves U to a Heisenberg group, and the omega size extends to the Heisenberg group. So we take that quotient. So that's what we'll mod out. We'll mod out the underlying vector spaces by the vector space generated by those objects, and that's the quotient that we're going to work with. Okay, and it's naturally a module for G1 cross G2, or again a cover of it, and you know, again, everything works the way you would think. There's an action by iota 1 and iota 2, and that's the object for which the sort of how correspondence ought to work. That's what we're proposing. Okay, and the global analog of that is in the sort of standard way that one goes back and forth between the local game and the global game, and instead of modding out by U, one does an integral over U. So we replace the Jacquet module by an integral over U-adelic mod U rational against the character, and then we'll restrict to the embedded image to make an integral kernel. And if that's a lot to say, I have it written down on the slide. Okay, so that's the game. All right, so now I want to give the specifics, and I'll write down the exact integral in the specific context of the groups that we're working with. Any questions? Okay, so here we go. So I'm going to start with an odd integer greater than 1. That'll index the degree of the cover. And I will be working with split groups. So SOK will be a split orthogonal group, special orthogonal group. And the splitness in a certain sense isn't essential, but I'll say a little more. And SP2N will be a symplectic group, and I mean 2N by 2N matrices, if you don't mind me saying it that way. So those are going to be the groups at play here. And this object R minus 1 over 2, this number comes up a lot. So I'll call it R1. So if I'm at the 7-fold cover, R1 is simply 3. Okay. And this is the standard game, pairing an orthogonal group with a symplectic group by the tensor product. So I embed them in SP2NK. And we wrote that down a little more conceptually earlier in the talk. And so it's the usual tensor product given by corresponding to the usual tensor product embedding. So that's the first thing, the classical reductive dual pair. And for the second embedding, it's just a pretty mindless thing in the way that I showed you those exceptional theta guys, where you just take the groups and sort of brutally embed them in the bigger group. And here we repeat the SOK a bunch of times, R1 times with H and R1 times with the corresponding thing. So the matrix is symplectic. And then we have one copy of the symplectic group embedded in the middle. So the symplectic group just gets left alone, and the other orthogonal group gets replicated, and that will turn out to matter. And the reason it matters is because we're going to be working with covers. And so one needs to keep track of the way that covers work with respect to embeddings. And the fact that I have R minus 1 copies of a group and it's the R-fold cover basically means that when I restrict the embedding of the R-fold cover of the big group to the smaller group, I get once again an R-fold cover of the smaller group, which would correspond to the inverse of the Menicky symbol or Hilbert symbol. So the fact that this is repeated a bunch of times does play an important role in making the construction work. Okay. So let's see. So I owed you as well a unipotent group and a character. So those are on this slide. So the unipotent group is simply the unipotent radical of a parabolic subgroup, where I take, say, GLK repeated R1 times in SP2N and embed that in the bigger symplectic group, which is SP2N plus K times R minus 1. So some bigger symplectic group, and maybe the simplest thing to do is visualize it for R equals 7. And so here it is in front of you. Okay, so I have the symplectic group in the middle. And anyway, so that's the unipotent subgroup. And then the character is the sort of standard kind of thing that you would work with, where you would take the trace of the K diagonal above the main diagonal in a K by K block sense. Okay, and to speak about it a little more conceptually, this corresponds to, once again, a unipotent orbit, which has a partition attached to it. And if you check it, you'll see this is the unipotent orbit r minus 1 to the k times 1 to the 2n. And you know, when I write raised to the k, I mean, this is a partition sense. So I repeat r minus 1 is repeated k times, and 1 is repeated 2n times. That's, of course, what the notation means for that partition. All right. So there's a unipotent group and a character. And then I also need to move the group in, I have to move from the unipotent group to a Heisenberg of the first symplectic group. So I have to weave the two symplectic groups together. And the way I do that, so the character only saw the sort of this part of the unipotent group, but we ignored the middle of the unipotent group, and there is a character there, but it comes through the Heisenberg. And so that subgroup of the unipotent group, which is in front of you, is isomorphic to a Heisenberg group in a natural way. And so you can take L by first projecting from U to this group, it's a quotient, and then taking that subgroup and or quotient group and mapping it to a Heisenberg group. And so that's the way you get the map L, which takes this unipotent group inside of the second symplectic group and moves it to a Heisenberg group of the first symplectic group. Okay. And so here we go, and we can make the correspondence. So we'll be working with a number of field containing the R-third subunity and A its ring of Adels. And just a comment about that, R is odd here. So our fields, of course, automatically therefore contain the two R-third subunity as well. And if you look at Marty Weissman's description of the L group, there's sort of a subtlety, not sort of, there is a subtlety when the field contains the R-thirds, but not the two R-third subunity. And so that doesn't appear in this construction. Okay, so there's a bit of a richer story that's not coming up in our case because R is odd here. Okay, so the small representation, which I called theta 2 in my general setup, in this case, is like the thing I was mentioning before. It's a residue of an Eisenstein series globally, or you can describe it locally in a similar way through intertwining operators. And so once again, that's what it is. And in a similar way to the other objects I was talking about, it's a representation that's very far from generic, but also is not attached to the minimal coadjoint orbit. Okay, and I think I mentioned this, the construction involves keeping track of covers and projections. And so we have to work with the cocycle, which Kudla described for the classical vague representation using the Rao cocycle. And then both Shuichiro Takeda for the double cover and the Yahl Kaplan in general have very, very careful descriptions of embedding groups in others. And so we're going to follow that work. And in particular, Yahl really took our doubling integrals and generalized them to covering groups. And it's very delicate. It took 125 pages for the first paper to do it very carefully and to keep track of all the cocycles. And locally it's easy, but when you do it globally, you have to change local cocycles by co-boundaries before you can take the product to make it all work globally. And so he has it very carefully done. And so, for example, in his work, when you take the big group and you take the two smaller groups embedded in it, they have slightly different cocycles it's the same group up to a co-boundary, and you have to keep track of that. And so his work was very, very helpful. And in a similar way, you'd start with a delic group, a delic big group, and you can restrict, and that makes everything work. And you keep track of the cocycles. So I'm omitting a certain amount of mess by omitting all the projections and covers in that, but it all works. And it's written down carefully in our paper. It takes a number of pages. Okay. So here's the global integral that we write down. And there's some little indexing thing that we're going to start with something on a symplectic group. And in this particular case, we'll move to the orthogonal group. Of course, you could go the other way around. And so you either have the R-fold or 2R-fold symplectic group, depending on whether you're going to go to an SOK where K is even, you would have the R-fold case. And if K is odd, you have the 2R-fold case. So there's some index kappa in this, and it's just a bunch of symbols. So if you don't really want to parse it, don't worry about it. But the key features are here that we're doing the adelic mod rational integral against the unipotent group, and we have the unipotent group embedded in the second theta representation against the character and moving in the first theta representation by means of this isomorphism or homomorphism, not an isomorphism, homomorphism that moves L to a Heisenberg group. The theta kernel involves two different theta functions. So that's the tensor product. So there are two different theta functions involved in the theta kernel. One on the double cover, that's a classical theta function that you might see in the classical theta correspondence going back to Siegel and Weil. And then the other one is this exotic theta function on an R-fold cover that's attached to a small but not minimal theta representation. And of course, you vary the theta functions over the space, and you do these integrals, and out pops something on SOKR, which is automorphic, and you can study that integral. So that's the object to study. Now, you might ask what happens for the one-fold cover. And in the one-fold cover, this group U turns out to degenerate. It's the trivial group. So there's no unipotent integration. And of course, here I would want the theta function on the one-fold cover that's small, and that's the trivial representation. So for the one-fold cover, there isn't a theta R, and there we're simply writing down the classical theta integral. So this really is a generalization of the classical theta correspondence, an extension of it, and you might think that the classical theta correspondence is the one-fold case of this construction that works for any odd R, but for R equals 1, it's much simpler. So that's the object. Okay, and of course you could do the lift going the other way. Our paper really focuses on this one, but obviously you could do it the other way as well. Okay, so let me describe a little bit more carefully what happens here. And so unipotent orbits for theta representations, I see I don't have the latest version of the slide I meant to give, but okay. So we might start out by asking a general question. If I take this procedure, which again you'll find in Kazhdan-Patterson, of taking an Eisenstein series on a covering group and taking its residue and constructing a theta function by the residue of a Borel-Eisenstein series, you might ask, what is the unipotent orbit attached to that? And so for covers of GLN, David and Patty showed that if you take a high enough degree cover, then in fact, the representation is generic. It's certainly not small. In fact, it's generic. And so you might ask, well, what if it's not generic? And then it turned out that Gordon Savin, quite a while ago, thought about this locally. We didn't know about it. And Yunxin Kai both rediscovered Gordon's work and then also gave a global answer. And they gave the general answer. And the answer is that if you take n and you divide it by r, you basically repeat r as many times as you can. And then what's left over is the partition is repeating r as many times as you can. It's simply then putting what's left over into the partition. So that's the answer. Okay, and that I meant to put that in the slide, but I think I maybe don't have the latest version. Okay, so for odd degree covers of symplectic groups, we have the following expectation that something similar holds. So if R is odd, then once again, first statement is that there's only one unipotent orbit that's maximal with respect to the property that there's a non-zero Fourier coefficient. This is a partially ordered set, and you can imagine that there's more than one maximal unipotent orbit, but we expect there's only one, a familiar expectation in the theory, and that basically the answer copies what's true for GLN, namely, it works out to be just the same thing. This first case is what you would have seen in GLN, and then that doesn't always turn out to be a symplectic partition, so you have to make a little bit of an adjustment when it's not a symplectic partition. So that's the conjecture. Okay, and I should say that the story with these studies of covers is even very interesting, and even in the case when it's generic, Fan Gao showed that there's a very beautiful local way of thinking about these, even when there's when it's generic, you can count how many Whittaker functionals there are locally, and it turns out that there's very interesting thing to say about their distribution. So there's also questions that raises in contexts like this as well. Okay, so here is a quick description of our main results. Okay, So first of all, we have to analyze this theta representation on the R-fold cover of this symplectic group. So if I look at the theta function, we're generally on the R-fold cover of SP2L, then we can fully prove the vanishing expectation for the Fourier coefficients. Namely, there are two classes of Fourier coefficients that vanish, namely the ones that are attached to unipotent orbits that are larger than the conjectured answer, and the ones that are attached to unipotent orbits that are not comparable with a conjectured answer. Okay, there's some local information as well. And then that's the vanishing property, and that's complete. But the non-vanishing, unfortunately, is not complete. And we do have a full proof for the 3- and 5-fold covers of the conjectured non-vanishing. And then we have some statement that you have, it works sort of part of the time that you have some statements. If you know SP2L, then you know SP2L 2 times L plus NR for any N. Okay, so there's some partial results, and the obstruction is really that we non-vanishing turns out to go ultimately back to the work of Kajdan-Patterson, and their work is global as well as local. And then Fan Gao was able to use those methods and in a very nice piece of work, really count and describe exactly when there's a Whittaker functional locally for a broader class of groups, and then it would be awfully nice to have that globally. And I sent some, Fan and I exchanged some email. I sent him this paper, and he wrote back saying he thought that maybe there might be some ways that could be addressed. So if he does that, that would be great, and I think that would be very helpful. But at the moment, the conjecture isn't fully proved. Okay, so we also prove a theta tower. And the theta tower statement is that the first non-zero occurrence in the theta tower is a cuspidal automorphic representation. So to prove something like this, you have to prove that the constant terms, of course, are 0. And so it's quite a lot of group theory to prove that the integrals corresponding to the constant terms are all 0. And so I won't go through it, but the ingredients that are involved are first of all, root exchange, a familiar method for analyzing these objects. And then sometimes you can use root exchange, and there are all these characters floating around. There's the psi u, and then there's the character that comes from the action of the Heisenberg group through the Weil representation. And if you can manipulate it so that you have a character that's non-trivial over an adelic mod rational group, then you get 0 from that. And then the last way to go is that you can sometimes manipulate it so that you have a constant term of the automorphic form that you were putting into the theta kernel, and that, of course, a constant term of a cuspidal of a cusp form is again 0. So those are the ways that you have to use all of those methods in order to show that the first occurrence is cuspidal. Okay, and then there's some local work, and in particular for equal rank and unramified principal series, we prove that the local theta map described above is cuspidal, where we use those twisted Jacquet modules that I wrote down. Okay, good. So, and again, functorial means Marty has a sophisticated version of L groups, but here we don't quite need all that structure. So it just means that I'd already mentioned that the dual group for the odd orthogonal group in the one-fold case is the same as what you would expect, but in the odd-fold case, but in the even-fold case, the long and short would swap, and it's the same thing on the symplectic side. That once again, the odd-fold cover worked just the way we learned that the dual group is an odd, or the complex points of an odd orthogonal group, but in the even-fold case, you still are in a symplectic. Okay. Now, when you do these things, it's I think worth mentioning that there's the structure here is very rigid, and so there's a dimension equality. And I wanted to mention that because, of course, the size of these representations plays a role. And so this really goes back to some observations of David Ginzburg from quite a long time ago. But just to flesh it out, in the case, say, where there's a functorial transfer, then our construction does satisfy a dimension equation. And the dimension equation relates 2 different dimensions that are part of the construction. We have all these groups, and they each have a dimension. And then we have all these representations, and they each have a dimension as well. And here, by dimension, I might mean dimension in the sense of Galfand-Kirillov dimensions, and maybe not everybody quite uses dimension in that context, but I know David was using dimension in that context, whoops, already in his paper in the Israel Journal in 2006. So, so the dimensions, again, you could just think of it as a half the dimension of O and so the dimensions of all these objects fit together. And so here's the dimension equation in this case, that the dimensions of the two representations, that the pre and post lifted representations, and the dimensions of the representations in the integral kernel equal the dimensions of the groups as well. And there's an account of how all this works, just to give a minute of advertising, that David and I wrote a paper where we extend this dimension equation just a tiny bit. And so in section 6 of this paper from last year, you can see more information about this. Okay, and so it's a little bit of a check, but you can check with that. And there's some work in progress here that the one thing we didn't do in this paper is to actually prove that somewhere in the tower, the lift is non-zero. And in fact, to talk a little bit more about when the first occurrence occurs, and so we should be able to show, we really plan and expect to show that if you start with a generic hospital automorphic representation of SP2nr, then there's always a non-trivial generic genuine lift to SP2n plus r plus 1. And in this case, so you would have, if it was the one-fold cover, you would have SP2n plus 2, but sometimes it goes down to SP2n plus 1, and there's an interesting story involving periods as to exactly when. And here the first occurrence sort of spreads out more, that if you're in the R fold cover where R is greater than 1, there are more possibilities for the first occurrence, and there's a richer description of exactly when that occurs, and it's pretty complicated. So that will be in a paper which we're working on, but it'll take some time, I think, to get completed. And we do expect, though by no means the work has been done on it, that this general structure should really extend the theta maps, which I talked about, which were also for very specific cover. That old work with Dan Bump and David Ginzburg, where we only worked with a double cover of autoorthogonal groups and maybe moving it to even orthogonal groups, but using a theta kernel and something on the double cover of an autoorthogonal group, that should of course be extended to 2R. And then the work of Spencer Leslie, and we think that those papers should be extendable to families of covers by means of a similar structure. Okay, now maybe just to conclude, I'd like to suggest that there is a broader paradigm at work. And the broader paradigm is a bit loose. It's just meant to be illustrative of maybe where one could go with this, that constructions in automorphic forms that work for algebraic groups or their double covers. We always have thought for years that a double cover is morally speaking an algebraic group, that or the double cover of a symplectic group, maybe to be more precise, that these constructions ought to extend to higher degree covers. And when I say construction, I don't just mean the formalism of L groups. I mean, that's very important, and Marty Weissman has really beautifully extended that formalism, but I'm saying that more than that, these physical constructions where you take automorphic forms and you do things with them, where you move forms on one group to another group, that those constructions should extend to covering groups much more generally. And so to mention some examples of this, Fan Gao, in his thesis, did a beautiful piece of work of extending Langland's work on the constant term of Eisenstein series to covering groups. He did it also in the language of Berlinski-Deligne covers, but there's an example of taking something and really extending it to a broad class of covering groups. Second example is these twisted doubling integrals that I wrote down together with David Ginzburg, Yunshin Kai, and Eyal Kaplan. Shout out to Eyal there. Can also be extended to cover. I imagine Yunshin is here. I can see Eyal on my screen. Anyway, so should also be extended to covers. And so I also mentioned that work of Eyal, and he really pushed it quite far of even getting L and epsilon factors in covering groups. And he was working with split groups, and then Yunshin Kai working with Berlinski-Deligne covers and dropping the split work, and doing the unfolding. So in these works, one can extend these constructions of covering of groups to covering groups, but it's a lot of work. It's really, if you look at these papers, they're not easy going. There's really a lot to do to make it work, but it does seem to be possible. And then, of course, our paper, which is the beginning of hopefully a big story of generalizing theta correspondences to covers. Okay, so that's a quick list of objects. And there's one big thing missing from a list that we all would think of. And well, there's two things. One is the trace formula, and I don't have much to say about it, but so I'll go to working with automorphic forms and spaces of representations. And so the last big thing to think about is maybe Langland-Shahidi theory for cover. And here it's not straightforward to extend Langland's Shahidi theory, because Langland-Shahidi theory uses Whittaker models. And for Whittaker models, there's not uniqueness for covering groups. It's not true even locally. The inverse image of a torus and the covering group is not abelian, everything breaks. But the proposal is that you should be able to generalize Langland-Shahidi theory to covering groups by replacing a cuspidal automorphic representation tau. If it was on a covering group, you would use the generalized Spey representation attached to tau. And that generalized Spey representation also comes up in Eyal's work and I guess in Yuanqing's work. So, there's sort of a drawback here that these generalized Spey representations are residues of Eisenstein series, and that theory is not as well developed as it needs to be. So they're mostly conjectural at the moment. But really, it goes back to a conjecture of Suzuki that a generalized Spey representation for a cover of GLN should have a unique Whittaker model. And we can expect a similar phenomenon more generally, a generalized Suzuki conjecture. And then the proposal is that you can take these generalized Spey guys and study Eisenstein series attached to generalized Spey representations, and that should permit an extension of Langland-Shahidi theory to metaplectic covering groups. And I know Erez, and I think it was with Zheng Mao, studied Eisenstein series attached to Spey representations, but now I'm proposing even doing it on covering groups. Okay, so that's a proposal, and we have to see if it works. And so I think I'm pretty much out of time, but thank you very much for the chance to be here. It's I have so many warm, wonderful memories of Rehovot, and I hope that soon I'll have a chance to see everyone in Rehovot, to see everyone attending the talk in Rehovot soon. And so here's a slide from one of my trips to Rehovot with a beautiful blooming tree and a little bit of scientific equipment in the background. Thank you. Let's see, I guess I should stop sharing and invite questions or comments.
Okay. Thank you very much, Sol. So any questions or comments?
So maybe I can ask you a quick question.
Please.
Yes. So in the last slide, I guess, when you talk about generalizing Langland-Shahidi, you mentioned the generalized Spey model, right, or Spey attached to tau. So is that something that is built from tau, like on a larger thing, as opposed to like something on a sub?
Let's see.
Like,
So,
with the,
yeah, I guess I'm thinking globally that you're going to take an Eisenstein series by using copies of tau R. Say tau is on an R-full cover, you'll use copies of it, and a suitable number of copies will be, let's see, should be on an even bigger. So you're asking, is that object on a covering group or on the group itself?
No, I'm asking because the Whittaker model of a cuspidal representation on G is defined using a subgroup, right? The maximum unipotent subgroup. But this generalized Spey models, you have to go to a bigger, right? An overgroup, so to speak.
Right.
Yeah.
So I'm
okay.
thinking of the rest of Eisenstein series.
Yeah, but is this just restricted to classical case? I mean, like suppose you have the E7 parabolic in E8, then what is one doing there?
I have no idea. I'm sorry. Yeah, I have no idea how any of that would work for for
okay. So you're thinking more in terms of classical groups.
right. So I don't
Yeah,
think that
okay.
this has been proved. Yeah, even for classical groups. And so I mean, some of the earlier stuff that I was describing of the generalized theta correspondence, of course, one can imagine doing that for exceptional groups. But this Langland-Shahidi extension, I mean, obviously, your question is very natural because a lot of bang for the buck with Langland-Shahidi theory comes from studying exceptional groups. And at this point, I think it's a vague proposal. I mean, I think that these objects haven't been created, they haven't been studied. You know, again, Dima and Eyal and maybe with Rami have some uniqueness results recovering groups, but I don't think they're as strong as what would be needed, if I'm not mistaken. And please correct me if I'm wrong. Don't mind at all. But so these, you know, there's a lot of conjecture here, and I don't really think I'm on firm ground making that conjecture for exceptional groups. But you know, one can imagine that something like that. So it's very vague, and I won't
Okay, thank you.
have to raise it as something to be investigated. Maybe that's the right way to say it.
Can I ask something? So could you relate the non-vanishing of the theta lift to the recent doubling construction of the L function, the non-vanishing of the special values of L functions?
I don't know of a relation, but I haven't thought about it much. But I don't know of a relation.
Do you expect the seesaw technique to work in this case?
A very nice question. You know, this is a few weeks old, and I don't know. Yeah, it's a very natural question. So it's a nice next thing, or one of the next things to do. Very nice. You know what could sort of say, yeah, everything should work, and maybe that would be a little bit like the philosophy, the paradigm. But since it hasn't been looked at, maybe the more cautious thing to say is that it's worth investigating.
Thank you.
You know, even for the exceptional theta correspondences, I don't think that the seesaw stuff has been, you know, for the non-minimal theta correspondences, I never really thought much about that, whether there is a natural way to talk about things like that. It's a nice question.
Yeah, so I'd like to ask a question. Some of the Jacquet modules that you were talking about really reminded me of similar construction we use for the doubling method. And the question is, do those theta lifts, do they come up naturally after the doubling construction, or is it conceptually different?
I mean, you know, I think in some ways, I mean, right, we see connections, and I think I would also say there's a connection to descent integrals, where you're taking you're making, you know, something which is again not generic, and taking you know, finding its unipotent orbit and looking at its Fourier coefficients and looking at the stabilizer of the character and restricting. I mean, I think it's in that sense related to descent integrals. So you know, I don't know what to say except there's the construction, and it's pretty new, and maybe you know, maybe there'll be some good theorems one can prove using it. Hope so. I don't know if I answered your question, Eyal, but good.
Yeah, so also regarding the Jacquet representations that Witek mentioned before, everything is still open even for GL, right?
Yes, that's what I thought. So Suzuki's conjecture is not known, and he frames it in terms of a generalized Shimura correspondence, which isn't known to exist. So, you know, it's really going out on a limb to say that all of this can generalize. And so to answer, you know, to go back to Witek's question, you know, exceptional groups will be particularly appealing, but there's just a lot that isn't known about these, even their existence of these things, and a generalized Suzuki conjecture, Suzuki for GLN, isn't known. But you know, one can imagine that that's all possible. And at least there's some evidence that lots of things extend to covering groups. But, you know, there's a lot to be done.
Regarding the vanishing results, you mentioned that you have a conjecture and you have some vanishing results. Are these all based on global analysis, exchange of roots, etc., or you also have local results, at least when data are ramified, or maybe even more?
Yeah, so we have some local results too. You know, somehow our motivation has been global, but that's maybe just our own, you know, set of priorities, if you will, and some of there are some local results in the paper, and certainly there probably can be more that should be done, and I think that's true for some other papers as well. So, you know, our focus has been on global results, and sometimes we need some local work to get the global. But I think it's a legitimate comment to say maybe we should simply do the local theory completely in parallel, and then we haven't done it as to the full end, and maybe there's more to be done there, is the right way to say it.
So when you look at the Archimedean places, you have to, when you formulate the global problem, you also formulate the local problem. Does that reduce to something we know? Because then usually the coverings are split over the groups.
Right, I haven't thought about that. I think, yeah, exactly. The global construction, there aren't any metaplectic groups, so that's sort of not as interesting to talk about. But maybe there's something, you know, maybe there's something good to be said, or something that has to be checked.
Yeah, I was thinking more of like a sanity check, that if things work, then they should, at least when things are split, they should give something that you know.
Absolutely, fair enough. Okay, thank you for all the nice comments.
Any further questions, anyone? Okay, I guess there were a lot of questions and comments. Thank you very much, Saul. I really enjoyed your talk. Thank you again.
Such a pleasure to see everyone. Take care, everybody.
Indeed, it's a pleasure to see everyone. The only advantage of Zoom talks, oh, there's one more that they're recorded.
There is still a way I can get you both to safety.
No jet lag.
All right, see you all.
Take care. Thanks for
Take
coming.
care. Okay.
Take care.
Take care, everybody.